So basically, the picture on the left is the univariate function or the well the space curve that you have seen already, right? For space curve, that you have only one parameter, then there's only one variable. Then let's say if you have your parameter or let's say your variable y equals f of x or something like t equals to, well, basically just rt, right? So in this case, we only have one variable, then there are only two directions that you can approach to that particular input value, okay? So, and then about continuity, and so the limits, we have the left-hand limit where your parameter goes to a, or the right-hand limit where your parameter goes to a. And then you need to also worry about the functional value at the point. Right. But then today we're going to see that for multivariate functions, let's say if you have x and y as the inputs, and we know our graph of the function is something in red, right, like a surface. But then to approach to a certain input point, like right here, and then you want to know the behavior about this function at this particular input point, then you need there are more than two directions. Okay, so on the left hand side, when there's only one parameter, then okay, actually you are lying on the line of the argument. There are only two directions, but then when we have x and y as variables, then it's a plane, right? So it's possible that you go along the x direction that's approaching these are already two directions, right? Now, if you think about the along the y-axis, there's gonna be two other directions that are perpendicular, and of course there could be other or weirder directions, like something like this. That's still straight, right? But there can be some curvy direction that just goes towards that point. So yeah, let me indicate that arrow here. It could be like zigzagging, right, approaching that point. So now it's kind of problematic that it's on a plane. So there are much more directions than just two. Okay, there are actually infinitely many of those. But let's put the things a little bit more formally. So recall for the univariate case, like we mentioned. So it's possible that sometimes the limit of the function exists at the point. So you will have an open circle that's indicating the functional limit at the point. Okay. So let's say our input level is A. So here you can see that when you approach A from the left and from the right, they agree. However, it doesn't agree with the functional value at the point. Right? So the big dot here, this is A f of A in this situation. So here the limit is represented by this notation that we have seen from Calc 1. So the limit when x, the input, approaches A for the function f of x, right? So of course, for a vector function, it's the same kind of notation. And the concept is also really similar because there's only one variable. So in this situation, the limit exists. Okay? However, f is not continuous because the limit does not agree with the functional value as x equals a. Okay? And of course, if the limit doesn't even exist, then it's definitely also not continuous. So the two possible limits that, let's say if they do not agree, and let's say the left hand limit is approaching to this solid point, well, the right hand limit is approaching something else. So in this situation, if you get an input close to A from the left, you will get to this solid point, which is the function value. If you approach from the right, then you at the open circle. So here we will see that the left hand limit is not equal to the right hand limit. So you see, we have the A, and then there's a super index negative sign, which indicates approaching from the left, right? If you put a plus, that's the super index at A, then this is the right hand limit. Okay, so they do not agree. So in this situation, the limit does not exist for the function at the point, and of course, f is not continuous. At the point. Right? So if we want the function to be continuous, we want to make sure that something like this happens. And at the same time, that the solid dot has to be filling the hole right here. Okay, so basically, if you're looking at this point, you can say this is where this is the point where our input is A, and the output is the limit of our function when the input is approaching A, right? So we must have the solid black dot to fill this open circle. So that's the definition of the continuity for a univariate function. Okay. So the left hand limits, the right hand limits, and the function value must all agree. So f of A in this situation has to equal to the limits of the function at the point. So this is the univariate function limits and continuity. And now if you think about the vector functions that we have discussed in the previous chapter, then it's really the same idea. Okay, so that's a little bit more formal review about what happens if there's only one variable. Okay, on the closed set right here. So the key remark is that we need to check the left hand limits and the right hand limits to determine whether the limit of the function when x approaches A exists or not. Right? So when you think about it, here the input A is actually lying on the real line, and then you're approaching this input point, and there are only the two possible directions you can go along this line. Okay, and we have to check both. But then for multivariable functions, it's going to be a little bit harder because on a plane there are infinitely many possible directions. It could be could be linear, could be not even linear, like a zigzagging that we have established a little bit earlier. Okay, continuity of multivariate function. So we mentioned at the beginning on the for the picture on the right that within the XY plane there could be all possible directions that can approach that input point, right? So for instance, let's look at this example. We want to study the limit. Now we have the input pair, okay? So this is now a pair of xy that's approaching some point in the xy plane. So let's say we're approaching the origin. And if we want to study the behavior of the function x squared minus y squared over x squared plus y squared plus. So and then if we think about all possible directions that you can choose, right? It could be something like straight, horizontal, or straight slant, like this, but it could be also something really weird, could be, or it could be zigzagging. Right. So here we start with some basic ones. Okay? So let us check the function values when the input pair approaches the origin along different passes. So basically, we'll start with the easy ones. Okay? So we'll start with the fundamental ones that are, let's say, along the horizontal or vertical lines, and then possibly, we need to check something that's a little bit more complicated. But then, basically, for the before we move on, for the univariate case, there are two possible directions that you can approach this input point, right? We have to, if you think about it, we have to have all the limits to agree at the point. Now, in the two-dimensional situation, then there are many possible directions. And of course, if one limit along a certain direction does not agree with the limits along the other direction, then definitely that's that function is not continuous. That limit does not exist, right? So the point here is that there could be many different kinds of directions. So it's kind of problematic. Well, yeah, let's just look at for this situation what happens. So let's start with the basic one. So if we approach the origin from the direction along the x-axis. So on the x-axis, that basically just says, okay, my y value is 0, right? So yeah, I'm gonna keep that function still right there. So for the plane, it doesn't have to be that large, but okay, along the x-axis, what does it do? So you have the y value to be 0, but then x could be free, but it just approach 0 also, right? So in this situation, in such case, y equals 0. Now let's denote that x squared. So this fractional function right here, let's denote it as f of xy. Okay? So f of xy to denote this functional fraction that we have. So then along x-axis, we can just plug in y equal to 0, okay? And let's see what happens. So f of x 0 equals to, so now we have what? We have x squared minus 0 over x squared plus 0. Right? So this is x squared over x squared, which is 1, which is a constant, regardless of the input. Right? As long as x is not 0, it's 1. Right? So basically, this is just saying, okay, I'm approaching the origin along the red arrows. And basically, at every point, it's gonna give me the same output. Then of course, when your x value approaches 0, the limit is also this constant. Okay? Hence, as the pair approaches the origin along x-axis, f of xy approaches 1. Okay? So now this is like a really basic direction, right? So that's good. Right. So if this is good, then now let's think about another direction. It's kind of clear that okay. So if you are along the x-axis, then y is 0, right? So that's what x squared over x squared. And now if you just switch to the y-axis, then you have x equal to 0 right here. Then oh, looks like there's a -1. So clearly, if you just choose the other really single direction, is going to give you something else. Okay, so let's write it down. Let us approach. So here you can see for this kind of question, there's indeed a lot of freedom of directional choice. Okay, but so that's what makes multivariate calculus hard in a sense. You always have freedom of choice. So here along the y-axis, x equals 0 now. And then we just plug in x equals 0. So we have f of 0y that equals to, so just like we mentioned, we have negative y squared on the top, y squared on the bottom, right? So you see, as long as your y is non-zero, it's always just a -1 for any y non-zero. So just following the same argument, so we know that as the point approaches the origin along y-axis, the functional output approaches -1. That was good. So now what can we say about this limit here? So if our point xy approaches the origin, in general, does the limit exist? No, right? So we just check 2. We just check the basic 2. But then these 2 doesn't even agree. Okay. We have different limits when approaching the origin from different passes. So the limit when our point xy approaches the origin of the function f of xy does not exist. Okay. So of course, when the limit does not exist, then the function is definitely not continuous at the point. Okay. Remark. So, like we mentioned, for a univariate case, if the limit on the left hand side does not agree with the limit on the right hand side, then the limit does not exist. Okay. But here, for the example that we have seen, we chose what? We chose the direction along the x-axis, we chose the direction along the y-axis, then the limits does not agree, then the limit does not agree. Well, the limit does not exist, right? So in general, you may pick some direction like this, you may pick another direction like this. If you have two different limiting values along different passes, then the limit does not exist, right? So somehow, we need to try a few directions before we conclude that the limit does not exist for a multivariate function. Example. So now let's look at the function f of xy that is defined. Well, it's really similar, but it's a little bit more complicated. So it's now x plus y holding square over the sum of x squared plus y squared. We want to show that the limit when xy approaches the origin of function f of xy does not exist. Okay, so now basically, if you just do eyeballing, right? So if you go along the x direction, you will have just make y equal to 0, you will have 1. If you make x equal to 0, you're just going along the y-axis, also 1. But then that does not guarantee the limit to be 1 for any other directions. Okay, so it could be something. If you pick a slant line, okay, it's gonna give you something else. Okay, so well, if you are familiar with this kind of process, it's relatively straightforward. But let's just put the things down. So that we know what we have to do when we see this kind of problem. So still along the x direction, x-axis, then we fix y to be 0. Okay, so let's just try the directions that we just mentioned. X-axis, we have what? We have y equal to 0. We just plug in. Okay, so f of x 0. Here y is 0, right? So we have what? We have x squared over x squared. It's again a 1 for x not being 0. So just be reminded that we always carry this this piece, right, for non-zero x values. Okay? Because that's basically what happens, that when you're taking the limit, you're not taking the input to be exactly that input value. Okay, you're just getting close, arbitrarily close, but never that value. Because here, for the fraction, you just want it to be always valid, right? And now we also mentioned that we approach along the y-axis. It's gonna give us the same thing, but we also just put that down. So along y-axis, basically along y-axis we have x equals 0, but y is free. So f of 0y gives us y squared over y squared, which equals 1 again. Okay. Y not being 0. Okay, so now we have 1 and 1, but this not necessarily tells you that the limit is 1 for other directions. Because like I mentioned, if you pick a slant line, then you can definitely see that the thing is different. Okay? Yeah, well, I said that sentence, but I want to put it down before I draw this another direction. It does not necessarily guarantee that limit exists, because by observation, right, you take a static line, maybe something different. So now let's think about y equals x. Okay, so basically, it's not gonna give you y if you have x equal to y, right? So when you have x equals y, you are along this line and you're approaching from the two pieces, upper and lower pieces, along y equals x. So along y equals x, it tells you what? It tells you the pairs. We have just x, right? We have the y coordinate equals x. So we plug in f of x, and then we have what? X plus x squared over x squared plus x squared. Now we actually have 4x squared over 2x squared. And now in this situation, we have a 2 instead of a 1 for non-zero x values. Okay. So this is definitely a different limit. Making sense? Any questions? Okay, now if it's all good, then we can still conclude that we got the conclusion that we want. Okay, so we have a two that's different from the previous ones that we got. Okay, limits. So limits doesn't to the origin does not exist for this function. And now, okay, so in this example, we have seen a slant line y equals x, right? Well, it's possible that you may see some more complicated fractions, and then you probably have to check more than two directions, okay? Something, so let's look at the example, f of x y equals to, still, it's a fraction, but it's x, it's x squared times y over x to the 4 plus y squared. We want to investigate the limit when x, y pair approaches the origin of this function f of x, y. So now let's see what happens for the directions that we have tried. So firstly, of course, along x-axis, what happens? Along y-axis, what happens? And along let's see, along x-axis. So here we have y equal to 0, so f of x 0. This equals to, so y is 0, so we have a 0 over x to the 4. Right, that's a 0 for x not being 0. So now, so basically this just says, okay, when we approach from on the x-axis, it's always going to be a constant. And if you do that along the y-axis, you can imagine it's the same thing. So the expression is a little bit different, but it's constant 0, because if you plug in 0 y, so we have what? We have 0 over y squared. Okay, so the expression is a little bit different. Yeah, let me put that down. So although it's a 0, but it's just 0 over x to 4. 0. Okay. So here, so this fraction now it's kind of a trivial zero. It doesn't matter that much, but there's a difference. Okay, so and here, okay, so now we have two zeros. Either we conclude that the limit is always zero on any other directions that you can possibly find. Or if we find the direction that gives you a limit that's non-zero, then we're done. Okay, we'll conclude that the limit does not exist. Right? And then, so now let's try the third direction that we have seen, which is the slant line, y equals x. So if we have this line, and then we're approaching from the upper and lower piece. So let's see, along y equals x. So here we have f of xx that we plug in, right? So here we have x to the 3. So now y equals x. So then we have what? We have x to the 4 plus x squared. Okay, now this is not a trivial zero, right? So we see when our x value is not zero, then we have a common factor of x squared on both top and bottom, right? If we cancel that out, we have x over x squared plus 1. So we see, okay, this is not trivially zero, although it will approach zero when we get x towards zero, right? But at least we know that this is not a trivial zero. These are trivial zeros. Okay, so in a sense, you can somehow expect, okay, it may behave a little differently if we just choose a different direction. So let's choose another slant line, but we have a different slope. So let's say now in this situation we have slant line. Let's y equals to m times x. Okay, so y equal to m times x. So it's a different slope where we just have a parameter that m that's representing the slope. While in the previous figure we have y equals x where the slope is just 1. Okay, along y equals mx. So we plug in what? We plug in x, m times x. Okay, now let's see. So we have x squared times y, which is mx to the 3 over, it's still x to the 4 plus y squared. Y squared is m squared x squared. Okay. And you can see it's relatively similar. It's just now we have an m on the top and m squared on the bottom, right? But then we still can cancel out the x squared that's in common. Mx over x squared plus m squared. So in a sense, now if you look at this, on the top you have x over x squared plus 1. That's just a function that's approaching 0. This one is still approaching 0. But now you see on the top the degree used to be 1 right here. If you think about the polynomial expression, right? So this x has a degree 1. But now if we think about m times x, that's actually degree 2. And here the terms are also degree 2. Okay. So this definitely tells you if you play it a little bit differently, it will give you something not 0. Okay, so this is still a 0. But now let's we can think about making so this m. If you think about this m, this is something unknown, right? So if we use it as a constant, it's just m times x. That's giving us this. But if you choose it to be what? If you choose it to be x squared, so if you choose m to be just x, right? That's gonna be something else. So along y equals x squared now. So let's quickly calculate that. So if we have y equals x squared, now we have what? We have x squared times y, right? X squared times y. Now y is x squared. And we have x to the 4 plus y squared. Now y value is x squared. Now this is you see, modifying from here to here, we just replace m by just x, and we actually get a 1/2. Right, so this is x to the 4 over 2x to the 4. So this is 1/2 for x not being 0. So now we have a direction that is actually is quadratic, right? It's quadratic, but it's somehow motivated. It's highly related to the line that we established. And now we found the direction that's giving us the limit that's non-zero. Okay, now we know. We have 0, 0, 0, and 1/2. Okay, the limit does not exist at the point. And this curve is actually y equal to x squared, which is quadratic. So this is a path like this. So, any questions? Here, let me give the conclusion. So, the limits when the point xy approaches the region of our function right here does not exist. Okay. So, as you can see, at first we have 2 directions that we checked, then we have 3 directions that we checked. And now in this situation, it's kind of more complicated. It's a fraction that we are now, it's a fractional function, and we have tried 4 different directions. We have, wait, 5, right? X-axis, y-axis, the line y equals x, y equal to m times x, which is a slant line with a slope m. And finally, we see, okay, we can make that m to be just x, and then we have y equal to x squared, which is a quadratic curve instead of a linear. So yeah, well, indeed, it's getting more and more complicated. So you can see that for bivariate case, to approach to a point, you have, well, actually infinitely many choices of directions. So it's indeed getting messy. So I would like to mention, for this kind of question where you have a fractional function and you are trying to determine whether it's continuous or not, whether the limit exists or not. So well, in the exam or on the quiz, I wouldn't really expect you guys to use complicated directions like these. Okay, so you can always try to find two straight line directions that will give you different limits. So that's about that. But then the point here is not really about being so creative that you find all kinds of different directions. Here we want to make the things a little bit more standard and more universal. When does the limit exist? Okay, so this is now the big question. The challenge here is that, okay, we have seen there are different kinds of directions that we can choose, right? So either we want to check all kinds of directions and we always got the same limit, or we just get something, we just do something else because there are infinitely many directions that you can check. Okay, it could be curvy directions like the ones we have seen, or it can be something really weird, like zigzagging or just circulating towards that point. Okay, so here the big question becomes the question: when does the limit exist, right? So to put that down in a picture, for the point AB, there could be directions like this, directions like this. So the quadratic one is really similar to this curvy direction, right? But then the directions could be zigzagging all the way down, like right here, or it could be circulating, right, getting close. But now, if you think about all these possible directions, what do they have in common? So actually, when they approach the point AB, well, it's obvious that they're getting close, right? By getting close, I mean, if you just draw different circles that have the center at AB and have a radii being smaller and smaller, regardless of the radius, a path will just pass through all these circles towards the solid point at the center, right? So let me write that down. All passes will pass through and go inside the circles centered at the point AB. Ultimately, no matter how small that circle is. No matter how small the radius is. Okay. So although the passes, they can have all kinds of weird directions, it could be something really crazy, but eventually it will get close to the point, okay? So the distance is gonna, so basically if you think about this, right? So it's not really about the passes anymore. We eventually, when the point is approaching the solid point in black, it will pass all those circles and get close. So it may not, so if you think about the distance from the point when it's traveling along the direction, it may get close and then further away and then goes back to the point, and it could be something really weird. So the distance may not be monotone in a sense, but still, if you eventually want to get close to that black dot, you still have to pass all these small circles. That's the point. So now we can motivate, we can directly write down the definition of the limits of the function, okay? Definition. So if you think about it, it's actually a generalization of the epsilon delta definition for the limits of a univariate function. But now we're just doing it in a multivariate case. If for any epsilon greater than 0, there exists a delta positive such that for any xy pair in the domain of the function f of xy that satisfies so basically when we talk about this kind of functional behavior, we're just saying, okay, when the input is getting closer and closer to the point AB, the output of the function is getting close to the limit. Okay, so that's now when you think about the distance, it's always just the distance between the point xy and the point that you want, okay, the input point AB. So we're just writing it in the vector form. But when we say it's close, then the point is different from the point AB, but then it's within the delta, well, the radius. Okay. So this magnitude is exactly the distance from the point A, from point xy to point AB. Right. So for any xy in the domain that's close, sufficiently close to the input point, we must have the functional value f of xy minus L is less than epsilon. Okay. So that's the epsilon delta definition that we have seen. So basically, this is just saying, okay, as long as your input point is within delta distance from the data point AB, then your output is epsilon close to the limit, capital. Okay. If that's the case, then the limit exists and equals to capital. Right. So you see, this is exactly a generalization from univariate calculus. Okay. So in univariate calculus, if you think about it, this is for any epsilon positive, you always have a delta such that when x minus a is within the delta distance, then functional value f of x minus the limit capital is within epsilon. Right? But this is exactly this generalization. So the only thing different here is that this is a two-dimensional distance, and then our function here is multivariate. It's a two-variable function. Remark. The above definition can be generalized, well, or can be extended to functions of let's say n variables. So now we have bivariate case, right? But then in general, if you have n variables, then you just say, okay, the input point x1 all the way up to xn is within the well, delta distance from the data point that you are approaching to, right? And then as long as your function value is within epsilon, then your function is good. Another remark. Using the above definition, we can prove, so we will not really prove it, but we can prove that if f of xy is a polynomial function, then it's going to be continuous. Okay. A polynomial function is really nice in this sense. Okay. If your input is xy is approaching some point a b, then the polynomial function is always continuous. And the limit exists to be the functional value at the point a b. Also, if f of xy is a rational function, and AB is in its definition, in its domain, then it's the same thing. Okay? So if you have a rational function, as long as your point AB is within its domain, as long as AB is a legal pair for the function f of xy, then it's the same thing. So the limit at the point equals to the function value. So the function is also, the limit exists and the function is continuous. Okay. Therefore, polynomial and rational functions are continuous at any point A, B in the domain. Now, we know that if the function is well defined, either it's a polynomial function or a rational function, you can just take the input pair and just plug in. Okay. So that will be really simple calculation. So let's look at some examples. Let's say our f of xy is a polynomial. So basically, a polynomial is a summation of a bunch of monomials, and for every monomial, you just multiplication of x to a certain power, integer power, multiplying by y to another integer power. Okay? And I should even say a non-negative integer power. So x squared y squared plus x squared plus xy plus 2y. Okay. So it consists of a bunch of monomials, and each one of them has a copy of x raised to non-negative power multiplying by y raised to another non-negative power, integer power. So, well, although it's not really important in this case, but well, non-negative integers, they are called what, natural numbers, right? So that's a polynomial. And so now a polynomial is well defined in the sense that you can just so the domain is the entire xy plane, right? So no matter what point that your xy pair is approaching to, you just plug that in. So if I'm evaluating the limit when xy pair approaches 1, 2, then the limit of the function is just exactly 1, 2, okay? So plugging this x equal to 1 and y equal to 2. So this is just 1 squared times 2 squared. So x is 1, y equal to 2. Plus 1 squared plus 1 times 2 plus 2 times 2. And so basically we have 4 plus 1 plus 2 plus 4. Okay. So that's 11. And really similarly, if we have a rational function, which is actually just a quotient between two rational polynomial functions. Okay, so if you see this is the example that we have done already. So x squared minus y squared, that's a polynomial, of course. Over x squared plus y squared, that's another polynomial in the denominator. Okay. So this is what's called a rational function. We have seen this one when we take the limit when the xy pair approaches the origin, right? So this is a rational function. This is a fraction of polynomial functions. So what do we know? So we know that for the domain, we don't really want this denominator to be 0. And you know that x squared plus y squared, it could be 0 only at the point x equal to 0 and y equal to 0, right? So we have a sum of squares. So it will be always positive unless both x, y are zeros. Okay? So the origin is the only point at which your function is not well defined. Okay. And then if you think about the point 1, 2, right here. If you think about 1, 2, it's definitely in the domain of the direction. So that tells you what? It tells you you can take the limit where your xy pair goes to so here, let's just do 1, 2. Of our function right here. So this is exactly with evaluate. Okay. So 1, 2 is in the domain. So when x is 1, y is 2. So that's going to be what? That's going to be -3 over 5. So basically, you can see that as long as your fraction, well, or the polynomial function, they are well defined at the point that you're looking at, then you can just evaluate at that point. So here, recall. So this result about the fractional function, this rational functions, we have seen that at the earlier stage of this section, the limit of this rational function when xy approaches the origin, this does not exist. So this fact doesn't really contradict to the result above about the point evaluation, because once again, this point 0, 0, this is not in the domain. Okay. So if 0, 0 is a legal point for this rational function, then of course you can just plug in. But now here, 0, 0 is not legal, so we not really apply this kind of evaluation there. 0, 0 is not in the domain. So this tells you what? It tells you basically when you're looking at a polynomial, well, a polynomial is always fine. Okay? But for a rational function, we need to be careful about those locations at which the function is not well defined. And basically, that's exactly where the domain, the denominator of the function is positive 0. So you can see that there isn't really a lot to emphasize about this beginning concepts. So that's the limit, right? So when you take the limit of a fractional function, just be careful. Okay. If you realize that the point that you're approaching to is not really a legal point, then it's possible that you can find a couple of directions at which the limits will be not the same, okay, will not agree. Right. But then if the point AB that you're approaching to is actually within the domain of the function, okay, that's just the evaluation here. So then we can talk about continuity. So definition. So basically, once we define the definition of the limits of a multivariate function at the point, then the definition of continuity is just going to be direct generalization as well. Okay. For f of xy, the bivariate function, we say this is continuous at a point B if the limit when xy approaches a b of our function equals to the function value at the point. Okay, so this is exactly what we have seen from the univariate case. Okay, so the only difference here is that in the univariate case, when you have a function f of x and you the limit it's continuous if your limit at the point exists and equals to the function value at the point, right? But here, the only difference is that we have a pair of the inputs, and then for this limit on the left hand side, there will be infinitely many kinds of directions that you have to watch out for. So that's why we you can recall that we motivated this kind of limit by doing the epsilon delta definition, where the xy pair just gets arbitrarily close to the point A. Right? So, but of course, we can continue talking about continuity within the domain, and so we say f of xy is continuous on cap D, the domain of the function, if it is continuous at any point in the domain D. And finally, we say it basically if f is continuous within the entire R2, in the entire R2 plane, then this function is continuous. Just we just abbreviate, omit the domain in this case. So if f is continuous in the entire xy plane, the set R2, we say that f is just continuous. Okay. So basically, if you think about a polynomial function, then it's definitely just continuous, okay? Because so the domain actually includes the entire xy plane, and then at any point, the evaluation of the function evaluates it will equals to the limit at point. So remark. Polynomial functions are continuous. And then rational functions are almost as good. Are continuous in the domains. Okay. Example. So just the proof of concept. So let's define g of xy as the following piecewise defined function. So x squared minus y squared over x squared plus y squared. So it's still the same rational function that we have seen from before. So this we know that this function is defined at any point not being the origin, right? So basically, as long as the pair xy is not the origin, then this fraction is well defined. Okay. So now let's say at the origin, let's define the output to be 0. Okay. So this piecewise defined function is a little bit different from the original fraction in the sense that the original fraction will not have the origin as a legal input. But now for this g, you see, at the origin we do have output that's 0. Okay, so here the domain of g is the entire R2. However, although we extended the domain of the fraction in a sense, but that's just making this function not a rational function anymore. Okay, So for the rational piece, it's continuous. But it's not on the entire domain, okay? It's on the domain that's excluding the region. So here, this slash just indicates that this is a set minus. Basically, you have the prior set R2 minusing the set that's containing the origin. So this exactly represents all the XY pairs that are not the origin. So basically, either X is non-zero or Y is non-zero. So this is another way of just excluding the origin from the XY plane. So if you write out the XY plane excluding the origin in either the way on the left hand side or the right hand side, then we know, okay, this function g of xy is continuous on this restricted domain. And we know it is not continuous at the origin, even though we fill up the whole of the functional value of the point. So this is really similar to the situation where you have the univariate function on the two sides, you have different limits, right? But then you just put a solid dots there to define the function of it. So it's not continuous since the limit when xy approaches the origin of our function does not exist. So when your function when the limit of the function does not exist, then even if you fill out the domain, it will not really help anything. Okay. See previous examples. So, and basically, you see, as long as we know how to take the limit for the rational function and polynomial functions, and also how to, as long as we know how to determine for this kind of rational function, how to determine whether the limit does not exist, then that's pretty much all we need to know about the limits and continuity for a bivariate function. So any questions so far? So you see, for today, it's mostly just generalizing what we have seen from Calc 1, right?